Okay, I'm Ritwik, and today the topic is metallurgy or principles and process of isolation. Uh, I hope I'm clear. Metallurgy topic comes like by heart topic, extremely theoretical topic, మొత్తం బట్టి except for one conceptual thing, Ellingham diagram. మిగతాదంతా బట్టి uh, I I hope I can post the trick booklet for this, but I don't have that right now. So let's carry on to the stuff. I just pasted some of the stuff in the NCRT and I'm gonna mark the important things in that this highlighter. So let's uh, so in the first table, aluminum, you're gonna have bauxite ore. Anyways, this table is important. Aluminum, bauxite is important. Iron, iron all four are important. Iron all four. No, this whole table is important. అండ్ ఇంకా చాలా వేరే వర్డ్స్ ఉన్నాయి. సో సో for aluminum, bauxite is chosen, and for iron, mostly iron pyrites. Mostly the oxide ores which are abundant and do not produce any polluting gases. Okay, not iron, you're gonna use hematite or magnetite mostly. You're not gonna use iron pyrites because iron pyrites uses the on combustion, it's gonna produce the SO2, and SO2 is harmful for the atmosphere. But oxide ores में kalse, you won't be getting anything. You'll be just getting more oxygen or something like that. Uh, for copper, zinc, any of the listed use may be used depending upon the availability and other factors. Before, okay, that's something. Doors, you're gonna crush them, then you're gonna turn them into oxides. Ores, you're gonna crush them into small pieces, then you're gonna clean them. Normal basic cleaning. Cleaning has different ways, physical methods, chemical methods. Basically, preparing the ore. After preparation of ore, you're gonna turn it into oxide by two methods, calcination or roasting. Ore batti, you're gonna use each method. Oxide ayaka, you're gonna reduce that oxide into metal by more methods. Ellingham diagram, basically. Reduction of metals, you're gonna find Ellingham diagram and this, what do you say, gold and silver metallurgy process and like electrolytic refining, ఇవి electrolytic reduction ఇవన్నీ ఉంటాయి రిడక్షన్ ఇంటూ మెటల్ లో. తర్వాత యూఆర్ గోనా డూ రిఫైనింగ్, అక్కడ యూఆర్ గోనా హ్యావ్ లైక్ 10 methods or something. Distillation, purification, zone refining, uh, some seeding agents or something. Okay, so that's the process. First, concentration of force. Concentration of force ki you're gonna have physical methods, hydraulic washing, magnetic separation, and float flotation. Hydraulic washing is essentially based on the principle of uh, gravity separation. Like ఒక్కొక్క ఓవర్ ఇంప్యూరిటీస్ లో కొన్నిటికి you're gonna have కొన్ని are gonna fall faster. Like how do you say this? Some particles are subject to more force of gravity. Some particles are subject to less force of gravity. So ఇప్పుడు what do they do is they just keep an upward stream of water and దానిలోకి you're gonna pour some air. ఇప్పుడు ఆ వాటర్ కి ఇంప్యూరిటీస్ అనేవి స్ట్రక్ అయ్యి సారీ you're gonna pour the ore. Water ki ore lo impurities స్ట్రక్ అయ్యి your ore is gonna come out of the water. Basically cleaning with water based on the gravity separation. Magnetic separation figure says it all. If your impurities are magnetic and your ore is non-magnetic, or vice versa, your impurities are non-magnetic and your ore is magnetic, you're gonna uh, spread them on a conveyor belt. Last లో యాక్సిల్ కి ఒక లాస్ట్ వీల్ కి ఒక మ్యాగ్నెట్ ఉంటుంది. సో అట్లాగా మ్యాగ్నెటిక్ పార్టికల్స్ అన్ని ఒక కంటైనర్ పడతాయి, నాన్ మ్యాగ్నెటిక్ పార్టికల్స్ అన్ని ఒక కంటైనర్ పడతాయి. Float flotation is basically you're gonna use float flotation for sulfides. Sulfide ores ki you're gonna clean by float flotation. Float flotation ki you're gonna need a couple of things: float stabilizers, collectors. Okay. Okay, this method has been in use for removing gangue from sulfide ores. In this process, a suspension from the powder ore is made with water. With collectors and float stabilizers are added. Okay, there should be another thing. I don't remember. Basically, water తీసుకుంటాము. వాటర్లో you're gonna add the powdered sulfide ore. తర్వాత you're gonna add collectors. Collector's duty is to produce froth. Collectors are pine oils, fatty acids, xanthates, etc. They enhance the non-wettability of the mineral particles. And float stabilizers are creosotes and aniline. They stabilize the froth. అంటే froth is essentially నొరగ ఎక్కువసేపు ఉండేలా చూస్తుంది. Your నొరగ has the ore. Collectors enhance non-wettability అంటే లైక్ నొరగలో ఓర్ ఉండాలి అన్నది ఎన్ష్యూర్ చేస్తుంది. దేర్ వుడ్ బి లెస్ ఓర్ ఇన్ ది వాటర్. అదే గోనా డూ ఇస్ ఓర్ని పౌడర్ చేసి వాటర్ లో వేసి దే గోనా కీప్ ఏ రొటేటింగ్ ప్యాడిల్ ఇన్ ది వాటర్ అండ్ కొద్దిగా ఎయిర్ పంప్ చేస్తూ ఉంటారు, ఎయిర్ వాటర్ ఎక్సెట్రా. అండ్ ఆ ప్యాడిల్ రొటేట్ చేస్తుంటే ఇట్స్ గోనా ప్రొడ్యూస్ ఫ్రిక్షన్. బేసిక్లీ చినుకుతారు లైక్ మంచిగా, బట్ నాట్ ఇన్ లైక్ zigzag directions. It's just a motor. చినుకుతారు, నొరగ వస్తుంది. your నొరగ contains ore without the, and your water contains the impurities and oils and truth stabilizers, collectors, whatever you have added. నొరగని కలెక్ట్ చేస్తే you're gonna have your ore. Mineral particles become wet by oils while gangue particles become wet by water. So అందుకే your collectors are oils. Rotating paddle again acids in mixture and draws air in it. కొన్నిసార్లు you're gonna manually pump the air into the solution, but if ఒకవేళ స్పీడ్ ఆర్పిఎం కరెక్ట్ గా ఉంటే you're not gonna need to add the air. As a result, float is light in the skimmed off. It's in right for recovery of particles. Obvious. Sometimes it is possible to separate two sulfide ores by adjusting proportion of oil to water or by using diffusions. కొన్నిసార్లు in sulfide ores you're gonna have one or two sulfides. Like if the copper pyrites ఉంది, in your copper pyrites it is essentially CuS and Fe2S. రెండు ఉంటాయి. FeS2, sorry. CuS and FeS2. ఎన్ని ఉంటాయి? If you're gonna need only copper ore, there are methods. అయితే you're gonna adjust the proportions of oil to water, like ఎక్కువ ఆయిల్ వేయడం, తక్కువ ఆయిల్ వేయడం, or you're gonna add depressants. ఇక్కడ వేరే ఎగ్జాంపుల్ ఇచ్చారు. My bad. ZNS and PBS ఎగ్జాంపుల్ ఇచ్చారు. When you're purifying a ore of ZNS and PBS, represent is NaCN, essentially forms a complex with zinc. Zinc and a cyanide to complex form, it's going to stay in the water and you get your PBS in the form. Leaching is essentially a chemical separation. Basically, how do you say? Reacting the ore with highly acidic or highly basic medium. In case of alumina, leaching of alumina from bauxite, you're gonna leach it with NaOH. Concentration is carried out by digesting the powdered ore with the concentrated solution of NaOH at 473 Kelvin, 473 to 503 Kelvin at 35 to 36 bar pressure. This way, L2O3 is leached out as sodium aluminate, giving the impurities behind. Basically, you're not gonna get the pure ore. That's sodium aluminate process. Highly acidic or basic mediums. In case of alumina, you're gonna need highly basic medium because alumina is amphoteric and partly acidic ore. The aluminate in alumina is partly acidic due to the impurities present in it. Alumina itself is amphoteric. The aluminate in the solution is neutralized by passing CO2 gas and hydrated Al2O3 is precipitated. At this stage, the solution is sealed with freshly prepared samples of hydrated Al2O3, which induces the precipitation. వచ్చిన sodium aluminate ni you're going to pass it through CO2 to break up the complex and obtain the aluminate in a hydrated form. And a hydrated aluminate ni you're going to heat it back to get amorphous or pure aluminate Al2O3. Also aluminum. Other examples are that gold and silver. I don't remember the MacArthur forest cyanamide process. Purification of gold and silver. Basically, here you're not gonna do the basic acidic medium thing. You're gonna leach out the metal by forming a complex. NaCN or KCN as so, and these are the reactions. Pretty important. Your zinc is gonna get leached out. Like zinc and an impurity. So how do you say this? I think the reaction is self-explanatory. Gold to complex form చేసి you're gonna perform a displacement reaction with the zinc. So gold cyanamide కాస్త zinc cyanamide అవుతుంది. Extraction of crude metal from concentrated ore. Basically, you're gonna, how do you say? I already sulfide ores unte you're gonna convert it into oxide. A ore unna you're gonna first convert it into oxide except the gold and silver ores. Oxide ga convert cheyalante you're oxidizing it, then you're reducing the ore. Appudu the obtained metal is crude metal. It has impurities, but you're gonna have the metal. When the oxidation ki two methods, calcination and roasting. Roasting is done in reverberatory furnace. Calcination is done in both reverberatory and blast furnace. Calcination is essentially burning up the ore without air. Calcination involves heating when the volatile matter escapes, leaving behind the metal oxide. So that's me. Roasting is burning the ore in presence of air, or otherwise called as oxygen. Roasting, you're gonna need it for sulfide ores, and when your sulfide needs to turn into SO2, and your metal needs to turn into oxide. Oxides are easy to reduce than sulfides, so that's the thing. In roasting, the ore is heated in a regular supply of air in a furnace at temperature below the melting point of metal. That's important. Below the melting point of metal is important. Some of the reactions involved are those are examples. Uh, the sulfide also of copper are heated in laboratory furnace. If the ore contains iron, it is mixed with silica before heating. Iron oxide slags off as iron silicate, and copper is produced in the form of copper matte, which contains Cu2s and Fe. So it's pretty self-explanatory. Uh, Basically, you're gonna add SiO2 to obtain something called slag. For copper pyrites only, you're gonna have Fe2S also. That's gonna get oxidized into FeO. But you see. First rotation తర్వాత కూడా you're gonna have iron pyrites. FeO ni now you're gonna leach it out by using slag. Like you're gonna form it into slag by adding SiO2. FeSiO3 formate. That's gonna get clean. Copper pyrites after roasting is called as copper matte. The word is important. Copper matte contains of Cu2s and Fes. The SO2 produced is utilized for manufacturing of F2SO4. This big process. That's a reverberatory furnace, basically having no air supply. Reduction of oxide to metal, we're gonna do it by adding either carbon or CO based on the temperature of your based on the temperature. You see this reduction of metal oxides usually involves heating in some other substance acting as reducing agent, carbon or CO or even other metal. Even other metals are used in very rare scenarios, like your copper's bacterial leaching. The reducing agent combines with oxygen of metal oxide. Some metal oxides get reduced easily, while others are very difficult to get reduced. Basically, that's the theory of Hellingham diagram. Thermodynamic principles of metallurgy, essentially Hellingham diagram. Theory oledu, I gave some limitations. The graph simply indicates whether a reaction is possible or not, but it doesn't give the kinetic factors. Basically, that process could be a process flow. So, you're gonna have only one set of best ore, best reducing it. The interpretation of delta E is based on K. Thus, it is presumed that the reactants and products are equally. Usually, your metal ores reduction is a reversible process. It's not like a fast 100% irreversible process. కొంత ఓర్ ఉంటుంది, కొంత metal కూడా ఉంటుంది. That's the most general scenario. So there is an assumption taken in the formation theory of Hellingham diagram that the reactions are reversible. So ఇప్పుడు reversible reactions కి you're gonna use that whole delta G concept. Delta G equal minus RTL అంతే వాడతాం. ఒకవేళ irreversible అయితే you're not gonna have a minus RTL. Okay? It's just delta G of products minus delta G of reactions. Up you angle diagram cannot help you. You're gonna need the delta G values. I never saw a question based on that. So never mind. Uh, this is not always true because the reactant or product may be solid. Solid, however, it explains how the reactions are sluggish when every species in the solids is in solid state and smooth when the ore melts down. Okay, that's one thing. It is interesting to note here that delta H and delta S values for any chemical reaction remain nearly constant even on varying temperature. That's like an observed fact in case of metal oxides. So the only dominant variable in the equation becomes temperature. However, delta S depends much on the physical state of the compound. Since entropy depends on the state, it will increase if a compound melts or vaporizes. Molecular randomness increases on changing the phase from solid to liquid or from liquid to gas. Basically, కొన్ని ఎలిగ్రామ్ డయాగ్రామ్స్ లో యూ గోనా హ్యావ్ ఇట్ లైక్ దిస్. ఇక్కడ లైక్ ఓన్లీ ఒక్కటి ఉండకుండా యూ గోనా హ్యావ్ ఏ an upward shift. అప్పుడు this point is essentially that temperature point is either melting point or boiling point. Mostly melting point or okay, let me do it now. అది మెల్టింగ్ పాయింట్ అయితే this is gonna be boiling point. సో దానికి రీజన్ ఏంటంటే సబ్స్టెన్స్ ఈజ్ గోనా మెల్ట్ అప్పుడు డెల్టా ఎస్ లో దేర్ ఇస్ ఏ చేంజ్ ఇన్ ఎంట్రోపీలో దేర్ ఇస్ ఏ హై చేంజ్. సో యువర్ ఎలిమెంట్ డయాగ్రామ్ ఈజ్ a graph of delta G and temperature, right? Delta G of reaction. This is temperature. So delta S change వల్ల there is gonna be like sharp curves. ఓకే, ఇక్కడ ఎంజిఓ కేసులో అలాగా కనిపిస్తుంది. యూ కెన్ సీ దట్ mg plus O2 turns to MgO and Zn plus O2 turns to ZnO. Left loner, that's the element diagram for many graphs. Importantly, C plus O2 gives CO and CO plus O2 gives 2CO2. This is how it goes. O plus O2 gives 2CO2. First thing. Your secondly, 2C plus O2 gives 2CO. అదెందుకు పైకి ఉంది ఇది ఒకటే కిందికి ఉంది అంటే రీజన్ ఈస్ ఇన్ యువర్ సెకండ్ రియాక్షన్ యువర్ కార్బన్ ఈస్ సాలిడ్, సో యువర్ డెల్టా జీ ఈస్ లైక్ యువర్ డెల్టా ఎంజీ ఈస్ పాజిటివ్, సో యువర్ స్లోప్ ఈస్ నెగిటివ్. హౌ డు యు సే డెల్టా ఎన్జీ పాజిటివ్ అంటే డెల్టా ఎస్ పాజిటివ్ కదా, డెల్టా జీ అంటే డెల్టా హెచ్ మైనస్ టీ డెల్టా ఎస్. సో డెల్టా జీ వర్సెస్ టెంపరేచర్ గ్రాఫ్ లో యువర్ డెల్టా ఎస్ ఈస్ పాజిటివ్, సో యువర్ స్లోప్ ఈస్ నెగిటివ్. సో అందుకే సెకండ్ గ్రాఫ్ ఈస్ డిక్రీజింగ్. అండ్ ఎలింగన్ డయాగ్రామ్ లో దిస్ ఈస్ ది ఓన్లీ గ్రాఫ్ విత్ ది నెగిటివ్ స్లోప్. 2C plus O2 gives 2CO. మిగతా అన్ని దే గోనా హ్యావ్ పాజిటివ్ స్లోప్ ఆర్ జీరో స్లోప్ కూడా ఇట్స్ హైలీ ఫేర్. యా సో ఇప్పుడు ఏది రెడ్యూసింగ్ ఏజెంట్ కింద యూజ్ చేస్తామంటే at higher temperatures you're gonna use the second thing 2C plus O2. Basically your carbon is the reducing agent. Low temperatures లో your CO is the best reducing agent. ఎందుకు అంటే ఇప్పుడు ఒక టెంపరేచర్ లో మోస్ట్ నెగిటివ్ గిబ్స్ ఎనర్జీ వాల్యూ ఉంటే ఇట్స్ లైక్ గివింగ్ అవుట్ మోర్ ఎనర్జీ అండ్ బేసిక్లీ ఇప్పుడు ఈ రియాక్షన్ ని నువ్వు మెటల్ రిడక్షన్ రియాక్షన్ తో యాడ్ చేయాలి. ది ఓవరాల్ వాల్యూ నెగిటివ్ రావాలి అంటే నువ్వు ముందు ఫస్ట్ మోస్ట్ నెగిటివ్ ది చూసుకోవాలి. మేబీ యూ కెన్ డూ ది రియాక్షన్స్ విత్ బోత్ రియేజెంట్స్, మేబీ యూ కెన్ డూ ఇట్ విత్ నన్, బట్ ది బెస్ట్ పాసిబుల్ కేస్ వుడ్ బి ది లోవర్ గ్రాఫ్. ఒక పర్టికులర్ టెంపరేచర్ లో కింద ఏ గ్రాఫ్ ఉందో, కింద ఏ రెడ్యూసింగ్ ఏజెంట్ గ్రాఫ్ ఉందో, ది లోయెస్ట్ వాల్యూ ఆఫ్ డెల్టా జీ, that would be your best reducing agent. So low temperatures లో CO, high temperatures లో CO2, sorry, high temperatures లో carbon would be your best reducing agents. Low temperature in the sense అక్కడ ఇచ్చారు. In case of iron, low temperature is 500 to 800 Kelvin, high temperature is 900 to 1500 Kelvin. So these reactions are metallurgy of iron. Iron from hematite, I guess. Fe2O3 నుంచి this is the reduction reaction. ఇది and here. The middle figure is your blast furnace. Blast furnace is important, please look quick on. The reactions are important, the temperatures are important, everything is important. This thing has an impurity of limestone, CaCO3, and limestone is gonna get decomposed to quicklime CaO, which removes the silicate impurities of the ore as slag. Like ఇక్కడ CaO important reaction. CaO plus SiO2 gives CaSiO. This is slag. The iron obtained from blast furnace contains 4% carbon and many impurities. So reduction చేసాక you're gonna obtain the crude metal of iron called pig iron. Pig iron నుంచి you're gonna have many kinds of iron: cast iron, wrought iron, stainless steel, and many such things. Pig iron is your first step of iron thing, crude metal. Crude metal. So cast iron is made by melting pig iron with scrap iron and coke using hot air blast. This thing is important. Actually, everything is important here. I'm just marking the unique ones. It is slightly better than pig iron, slightly lower carbon content, and many other impurities are reduced. Physical nature is extremely hard and brittle. Further reductions like more pure iron is wrought iron or malleable iron. It's a purest form of commercial iron and is free from cast iron by oxidizing the impurities in the reverberatory furnace lined with hematite. This process is called puddling. This hematite oxidizes carbon to carbon monoxide. As it was, that reaction is there. limestone is added as flux. So basically, uh, see that. And sulfur, silicon, and phosphorus are oxidized and pass into the slag. So CaO plus sulfur SO2 is gonna give something like CaSO3 or something. అట్లాగా ఉన్న నాన్ మెటల్ ఇంప్యూరిటీస్ కి యువర్ లైమ్స్టోన్ CaCO3 is gonna act as a formation of slag. Slag ఫామ్ అవ్వాలంటే you're gonna add the flux. Flux వేస్తే slag ఫామ్ అవుతుంది. Your flux is the CaCO3 in this case. So the iron extraction, copper extraction, enriching reactions. Copper extraction, you're gonna do it from copper pyrites. ఎందుకంటే you don't have a very good copper oxide ore. So basically, copper roast చేస్తావు. Cu2S plus 3O2 is 2CO2, 2 Cu2O plus 2SO2. ఇప్పుడు రోస్టింగ్ కాకుండా ఇన్ కేస్ ఆఫ్ సల్ఫైడ్స్ లేదా లీచింగ్ కాకుండా ఇన్ కేస్ ఆఫ్ సల్ఫైడ్స్ you're gonna have a better method called self reduction. Leaching ante it's essentially using reduction by carbon or CO. That's the name. In case of copper pyrites, there is a method called self reduction. If copper sulfide ni heat cheste, you're gonna have copper oxide plus SO2 together. This copper oxide plus SO2. Wait, what? Okay, you can do this also. But self reduction, this copper oxide plus SO2, దీన్నే మళ్ళీ హీట్ చేస్తే యు గోనా హ్యావ్ కాపర్ బ్యాక్. Like ఇక్కడ SO2 acts as a reducing agent, your Cu2O turns to copper, your SO2 turns to SO3. That's one method. ఇక్కడ in these guys use the normal leaching method. I'm gonna answer self reduction though. Cu2O plus SO2 gives copper plus SO3. Unbalanced reaction. This is one method. Here they give another method. Normal coke to reduction, yes, sir. Coke ante it's essentially reduction at high temperatures. In actual process, you're gonna need a flux. So the impurities come off. In this case, your impurity is iron oxide. Iron sulfide which turns into iron oxide on roasting. Iron oxide ki you're gonna add the SiO2 slag. Okay, another point. SiO2 is a acidic flux. Iron oxide is a basic oxide కాబట్టి or SiO2 is an acidic flux. ఆ రెండు అప్పుడు they give the slag. If your impurity is basic acidic oxide, you're gonna add basic flux like CaO. ఇందాక కేసులో your non-metal sulfur oxide, sulfur, phosphorus ఇలాగా ఇంప్యూరిటీస్ ఉంటే those are acidic impurities కదా, you're gonna add basic flux CaO to get the slag. Copper matte is then charged into silica line converter. Basically, reverberate free furnace self reduction. Some silica is added and the hot air is blown. Hot air blast is blown to convert the remaining FeS, FeO, Cu2, SO, Cu2 to metallic copper. Following reactions take place. That's the thing. ఇక్కడ your crude metal is named blister copper because of its blistered appearance. అక్కడ pig iron, ఇక్కడ blistered copper. Zinc is interesting. Ikkada you're not gonna use self reduction or leaching. Ikkada you're gonna use electrolytic reduction. Basically, electricity to you're gonna reduce the ore. Zinc is mostly required in less quantities, so electrolytic reduction can be performed on a suitable scale. మరీ మాస్ మ్యాగ్నిట్యూడ్ ఎలక్ట్రో రిడక్షన్ అవసరం ఓవర్ అవసరం లేదు కాబట్టి it is feasible to perform electrolytic reduction. See, we think the reduction of zinc oxide is done using coke. Uh, the temperature in this case is higher than in the case of copper. For the purpose of heating, the oxide is made into briquettes with coke. Basically, carbon reduction. Okay, I bet. You wanna refine the thing with electricity. The metal is distilled off and corrected by rapid chilling. నా మెయిన్స్ క్వశ్చన్ పోయింది ఇది. Your zinc is distilled off. Electrochemical principles of metallurgy. Aluminium you're gonna like Al2O3 వస్తుంది కదా. You cannot use any reducing agent for it. It is too hard. Thermodynamically చాలా slow ఉంటుంది. So what you're gonna do is electricity. You say basically electrolysis. Electrolysis is using electricity to perform a chemical reaction. Your electrolysis is named as Hall-Herold process. Essentially, your anode is the I don't remember this. Anode is graphite rods inserted with the copper clamp. Cathode is the steel vessel containing carbon lining. Your electrolytes would be your Al2O3 and Al2O3 key. You're gonna add Na3AlF6 and CaF2 and or CaF2 your Na3AlF6 is cryolite, CaF2 is Na3AlF6 is cryolite. CF2 పేరు I don't remember. Okay, RS Na3AlF6 and CF2 are added because Al2O3 is still hard to electrolyze. Like the reduction ki custom, electrolysis ki custom because of Al2O3 is very high melting point and lack of conductivity. Na3AlF6 decreases the melting point of Al2O3. So basically easier to melting point I guess. CF2 add చేయడం వల్ల your conductivity is gonna increase. So easy heat generate. That's an important thing. So those are the reactions. ఇప్పుడు మనం గ్రాఫైట్ ఎలక్ట్రోడ్స్ వాడుతున్నాము అండ్ కార్బన్ లైనింగ్ వాడుతున్నాము. సో యూర్ నాట్ హ్యావింగ్ ఇనర్ట్ ఎలక్ట్రోడ్స్. బేసిక్లీ ఇక్కడ కూడా చేసేది రిడక్షన్ బట్ యూఆర్ యాడింగ్ ఎ డ్రైవింగ్ ఫోర్స్ ఆఫ్ ఎలక్ట్రోలైసిస్. Al2O3 plus carbon gives Al plus CO2. Your cathode reaction is the anode reactions are these Al plus C2Al, carbon to CO, CO to CO2. So that's how you're gonna reduce Al2O3. Copper key, you're gonna use self reduction or that roasting with leaching with coke. Carbon is called coke if you don't know. But మరీ లో గ్రేడ్ కాపర్ కి అసలు లో గ్రేడ్ కాపర్ ఎందుకు వచ్చింది అంటే ఇట్స్ మెథడ్ ఆఫ్ రీసైక్లింగ్ లో యూ గోనా హ్యావ్ లైక్ some content of copper, not rich in copper, but rich of waste and some kind of ఆర్ట్లో మళ్ళీ కాపర్ ఉంటుంది. కాపర్ is impurity లాగా ఉంటుంది బట్ ఇట్ డజంట్ మేక్ సెన్స్. స్క్రాప్ లో యూ గోనా హ్యావ్ ఎ లాట్ ఆఫ్ యూజ్లెస్ మెటల్ బట్ కాపర్ కూడా is considerable amount. So in the method of recycling you're gonna extract the copper in this way. Copper is extracted by hydrometallurgy from low-grade ores. It is leached out using acid or bacteria. This is not like conventional leaching out. Carbon, CO2, electrolysis varkunda, you're going to use acids or bacteria, normal chemical reactions and biochemical reactions.
The solutions containing Cu plus 2 is treated with scrap iron or H2 normal reduction reaction. This is highly chemical thing. Reduction of copper from low grade ores is called as bacterial leaching and hydrometallurgy. Oxidation reaction. You're not always gonna add your basic things like oxidize CC, reduce CM charges. Sometimes you're gonna just oxidize the solution to obtain the product. See this thing. Chlorine ని బ్రైన్ సొల్యూషన్ నుంచి ఎక్స్ట్రాక్ట్ చేయాలంటే you're gonna do that reaction thing. Besides reduction, some extractions are based on oxidation, particularly for non-metals. Example is brine from chlorine from brine. That's the reaction. You're gonna get Cl2, NaOH, and H2. That's the electrolysis of dilute NaCl, otherwise called as brine. If you're gonna use molten NaCl, మనకి NaOH కూడా రాదు. You're gonna get sodium metal and your Cl2 gas. And H2, no, Cl2 gas. This is because of that electrochemistry, electrolytic thing. Dilute దానిలో అయితే you're gonna have a possibility of having OH minus, so NaOH forming. ఇక్కడ your Na plus has to get reduced to Na. As stated earlier that McArthur for a cyanide process, ఇక్కడ your zinc is gonna act as a reducing agent and a complexing agent also, like a complex displacement agent. ఇక్కడ బేసిక్లీ ఆక్సిడేషన్ అవుతుంది, దట్ యూ కెన్ సీ ఆక్సిడేషన్ రిడక్షన్ కూడా అవుతుంది. కాంప్లెక్స్ ఫామ్ అయ్యేటప్పుడు ఇట్స్ గెటింగ్ ఆక్సిడైజ్, కాంప్లెక్స్ బ్రేక్ అయ్యేటప్పుడు ఇట్స్ గెటింగ్ రెడ్యూస్. ఫైనల్ స్టెప్. ఇప్పుడు చాలా మెటల్స్ కి యూ హ్యావ్ ది క్రూడ్ మెటల్ ఆఫ్ దట్ థింగ్. ఎక్సెప్ట్ గోల్డ్ అండ్ సిల్వర్. గోల్డ్ అండ్ సిల్వర్ లో గోల్డ్ అండ్ సిల్వర్ కూడా యూ గోనా హ్యావ్ ది క్రూడ్ మెటల్ కైండ్ ఆఫ్ థింగ్ ఇట్ సెల్ఫ్. ఇప్పుడు ఈ క్రూడ్ మెటల్ నుంచి you're essentially purifying the crude metal into something, into a more pure metal, so that you can use this for industrial purposes. Methods are these 6 methods. Okay, I remember 10. Distillation, liquidation, electrolysis, zone refining, vapor phase refining, chromatographic methods. Distillation is essentially for low boiling point metals. Like zinc. Every bit of this refining is important. Like examples are important. So I'm gonna try to mark this zinc and mercury. Pure metal is evaporated to obtain the pure metal distillate. Liquidation ante low melting point. Basically mercury, if I remember it right. Mercury you can do it by liquidation. Electrolytic refining is basically electrolysis. Aluminium, after you do the Hall Herold process, there is a process called Hoops process. Then you're gonna do the aluminium metal, you're gonna add it in the container with the same container, graphite electrodes and carbon lining. Then so aluminium, you're gonna add BaCl2 and CaF2 and NaCl brine, if I remember it right. ఇట్లాగా 2-3 వేసి you're gonna perform the electrolysis. అప్పుడు the crude metal of aluminium is more purified into your normal aluminium, pure aluminium. That's called Hoops process. That is an example of electro refining. That means reflection example చూద్దాము. Okay, some more points regarding electrolytic refining. There is a thing called anode mud. Let me just show it here. In this method, impure metal is made to act as anode. Okay, this is completely different. Hoops process is not exactly like electrolytic refining. Yeah, anode ni impure metal ni anode piece చేస్తారు. ఒక ప్యూర్ మెటల్ ని లైక్ సేమ్ మెటల్ ప్యూర్ ఫామ్ లో ఉన్నది క్యాథోడ్ కింద చేస్తారు. వెన్ యూ పర్ఫార్మ్ ది ఎలక్ట్రాలసిస్ లైక్ వోల్టేజ్ పెట్టి వెన్ యూ స్టార్ట్ ది ఎలక్ట్రాలసిస్ కరెంట్ ఫ్లోస్ అంటే యువర్ యానోడ్ ఈ స్లోలీ కొన్న డికే లైక్ కాపర్ అయాన్స్ ఫ్లో అవడం స్టార్ట్ చేస్తాయి. అప్పుడు యువర్ ఇంప్యూరిటీస్ ఆర్ గోనా జస్ట్ ఫాల్ డౌన్. సో ఇప్పుడు కాపర్ లో యూజ్ దిస్ అల్ట్రాలిటిక్ రిఫైనర్ కాపర్ impure copper anode, highly pure copper cathode అది పెట్టేసి నేను కూడా put up the voltage, కాపర్ రాడ్ అంతా క్లీన్ అవుట్ అయిపోయి అనోడ్ అంతా క్లీన్ అవుట్ అయిపోయి గొన హ్యావ్ ది కాపర్ అయాన్స్ డిపాజిటెడ్ లైక్ క్యాథోడ్ బల్క్ అయింది, యానోడ్ ఉండదు. ఎందుకంటే యానోడ్ ఉన్న కాపర్ అంతా క్యాథోడ్ కి వచ్చింది, యానోడ్ లో ఉన్న ఇంప్యూరిటీస్ అన్ని కిందకి యానోడ్ మట్లో వెళ్తాయి. And this anode mud contains like anode mud of copper contains rare metals like silver and gold. So the collection of anode mud is also an essential step in this metallurgical processes. We're gonna sell the silver and gold, make a profit out of it. So that's the thing. Your anode is impure copper, cathode is pure copper, your electrolyte is an acidified solution of copper sulfate. And the net result of the electrolyte is transfer of copper impure from anode to cathode. Impurity is from blister, copper, silver, gold, and platinum. Zinc is also refined this way. Copper key, there is an old way called logging or something. Polling. Basically, green tree logs ni pile up chesi, you're gonna put the copper in them. Like the blister copper key, the impurity is the copper oxide, CO. సో దాన్ని ప్యూరిఫై చేయడానికి అట్లాగా గ్రీన్ ఫ్రెష్ లాగ్స్ లో కాపర్ పెట్టేసి యుగన బర్న్ ఇట్ అప్. అప్పుడు ఆ గ్రీన్ లాగ్స్ బర్న్ అవుతుంటే యుగన గెట్ CO2 అవుట్ ఆఫ్ ఇట్. వుడ్ కంటైన్స్ కార్బన్ ని బర్న్ చేస్తే CO2 వస్తుంది. దెన్ యువర్ కాపర్ ఆక్సైడ్ ఈస్ గోనా గెట్ రెడ్యూస్ టు ఓకే CO2 కాదు CO వస్తుంది. కాపర్ ఆర్డర్ ఎందుకంటే యూ బర్న్ గ్రీన్ logs, you're gonna get CO. You're gonna burn dry logs like ఎండిపోయిన చెట్లు, ఎండిపోయిన కొమ్మలు వేసి బర్న్ చేస్తే you're gonna get CO2. పార్షియల్ కంబషన్ అయింది గ్రీన్ లాగ్స్ వేస్తే, ఫ్రెష్ గ్రీన్ లాగ్స్ వేస్తే. That CO is gonna reduce your CO2O into copper. That's not function in a zone refining. Let's see diagram. Basically ఒక ఓర్ ని ఒక మెటల్ ప్లేట్ ఒక సర్ఫేస్ మీద పెడతారు, అండ్ దట్ సర్ఫేస్ ఈస్ పుట్ ఇన్ ఎ కంటైనర్. ది హోల్ థింగ్ ఈస్ గెటింగ్ వాక్యూమ్డ్ అండ్ ఆ కంటైనర్ చుట్టూ హై టెంపరేచర్ ఉన్న రోలర్స్ పెడతారు. యుగన మూవ్ ది రోలర్స్ ఫ్రమ్ వన్ సైడ్ టు అనదర్. జోన్ రిఫైనింగ్ అన్నది ఎప్పుడు వాడతారంటే when the impurities are more soluble in the melt than in the solid state of the metal. You don't understand what melt metal is when you know solvent. Basically, metal ni impurity ni రెండింటిని మెల్ట్ చేస్తాము, and when you're gonna move the rollers, impurities are gonna stay in the melt. లైక్ ఒక పార్ట్ మెల్ట్ అయితే ఇంకో పార్ట్ కూల్ అవుతుంది కదా వెన్ యూ మూవ్ ది థింగ్. సో మూవ్ అవుతున్నప్పుడు వెన్ దిస్ థింగ్ ఈస్ సాలిడిఫైయింగ్, ముందు ఉన్న పార్ట్ సాలిడ్ అయిపోతుంటే యువర్ ఇంప్యూరిటీస్ గెట్ పుష్డ్ ఇన్ టు ది మెల్ట్. సో అట్లాగా మెల్ట్ లోనే ఇంప్యూరిటీస్ అంతా డిస్ప్లేస్ అయ్యి ముందుదంతా మెల్ట్ అయ్యి మెల్ట్ అయిపోయి మళ్ళీ సాలిడిఫై అయిపోతుంది. యూర్ గోనా డూ ద థింగ్ ఫర్ plenty of times, 5 to 6 times. Hopefully you're gonna get a pure metal rod. That's the thing. Example, germanium, silicon, your semiconductor electronics. Semiconductors, you're going to use the zone refining. Vapor phase refining is more like a chemical method. Vapor phase refining, you have two, three process. Bonds process, Van Arkel method. Bonds process is for nickel. Basically, this thing is for vapor phase refining. If refining, if you just something, when some derivative of the metal has very low melting point, like very low sublimation point. Seriously. Once process for refining nickel, okay, the metal should form a volatile compound with an available reagent. The volatile compound should be easily decomposable so that the recovery is easy. Basically, low sublimation point on a metal out kavali and metal derivative out kavali, and that metal derivative should be easily decomposed. Metal thing is easily decomposed. Nickel, when you form nickel tetracarbonyl, that is your most volatile thing. Nickel tetracarbonyl another when heat chest, it is gonna immediately become as vapors and that thing's gonna break into nickel and CO back. So impurities on a reactor essentially we're separating out the impurities. Separating out the impurities. Van Arkel method, same thing. It's a with zirconium and titanium, and your like agent is I2. Zinc tetraiodide, zirconium tetraiodide form అయితే లేదా your titanium triiodide form అయితే these two are more volatile and can break easily. I minus is a big iron and ZrI4 ante it's like I'm 4 iodines around small zirconium. It's not stable. When I break అయిపోద్ది and it's also more volatile for the same reason. Nickel tetracarbonyl కూడా same explanation. CO is a big thing. More attractions ఉంటాయి. Nickel cannot handle 4 CO around it at once. The metal iodide is decomposed on tungsten filament electrically heated to about 1800 Kelvin. Pure metal is just deposited on the filament. That's the Mons process and Van Arkel refining. I think that's important. Lastly, chromatographic methods. This method is used when your impurities and your ore has highly similar chemical properties. Asla ఏ ఫిజికల్ మెథడ్స్ తోనూ సెపరేట్ చేయలేదు, కెమికల్ మెథడ్స్ తోనూ బాగా సెపరేట్ చేయలేము అన్న కేసు వచ్చినప్పుడు యూర్ యూజ్ ది క్రోమటోగ్రఫిక్ మెథడ్స్. Chromatography is based on the like adsorption extent to the any particular solvent. Yes, ఏ కెమికల్ అన్ని కెమికల్ ఫీచర్స్ సిమిలర్ ఉన్నాయంటే we're gonna use the fact that maybe their adsorption extents can be differ. Adsorption extents కొద్దిగా డిఫర్ ఉన్నా కూడా you can pull out major amount of ore by chromatography methods. That's the thing. First definition again. Different components are adsorbed at different levels on the column. Later, the adsorbed components are removed using the suitable solvents depending on the physical state of. That's all. In one such method, the column of Al2O3 is prepared in a glass tube and the moving medium containing a solution of components using liquid form. This is an example of column chromatography. The picture is shown below. This is very useful for purification of elements which are available in minute quantities and the impurities are not very different in chemical properties from the elements to be purified. That's checking there. Column chromatography in which right side is fractional distillation. That's the fractional distillation column. Fractional distillation column is going to have the beads fractional distillators and holes fractional distillators. That thing is the beads one. Fractional distillation concept. It's going to come up in GOC and
not so much important in this method. Finally, some applications of the final metals we have so frequently obtained. Please read them. I can't. Important, important. Aluminum, so you're gonna have your lightweight components, your wrappers, foils, and some airplane parts. Aluminum being reactive is also used in the extraction of chromium and manganese from their oxides. Avi, you can't tell, so please remember. Maybe choose a good spot for Scani if you can't tell them out of thin air. Those simple reactive things. Wires of aluminum are also used in electricity conductors. Alloys containing aluminum being light are very useful to manufacture airplane parts, submarine parts, etc., etc., etc. Copper is used for making wires because of its very high conductivity. Silver has higher conductivity than copper, but silver is way more expensive than copper. So unless it's very necessary to have extreme conductivity, copper is used in place of silver. For water and steam pipes. Okay, that's reasonable. Your copper cleans the impurities in water to a higher extent with RO filters with copper, highly famous industries, right? It is also used in several alloys that are rather tougher than metal itself. Copper is a weak metal, so you're gonna have to make an alloy out of it with some other metals. For example, brass with zinc or bronze with tin, and coinage alloy with nickel. These things are more rigider than, more stronger, like more stronger than copper itself. And these have some surprisingly interesting electrical properties, and their physical appearances also differ. Like they, brass has a certain luster copper doesn't have. కొద్దిగా shine అయింది brass. Not brass, I think it's bronze. కొద్దిగా shine అయింది. These things, these copper alloys have wide applications. Zinc is used for galvanizing iron. It's also used in large quantities in batteries, electrochemistry. Remember the alloys: brass, german silver, bronze, coinage alloy, and you have some couple of alloys in other chapters also. Remember them. Used as a reducing agent, that's obvious. Zinc plus 2 is a strong reducing agent. Right, zinc is a strong reducing agent, not zinc plus 2. Manufacture of die stops paints that you have to remember. Cast iron, which is most important form of iron, is used to making casting stoves, railways, sleepers, gutter pipes, toys, etc. It is used in manufacture of wrought iron and steel. Wrought iron is used in making anchors, wires, bolts, chains, and agricultural implements. So basically, your not so strong, not so weak iron stuff is made out of cast iron. Your wrought iron is made for absolute density, like absolutely strong items. These anchors, wires, absolute iron requirements. You know? Steel finds a number of uses. Alloy steel is obtained when other metals have added to it. Nickel. Please read that whole thing. And the below the table is an important is the gist of the extraction of those metals. Aluminium, you're gonna use bauxite or cryolite. Cryolite you might not be used. Mostly you're gonna use bauxite. Cryolite water you cannot purify it more. Electrolysis of Al2O3 dissolved in molten cryolite. For the extraction, a good source of electricity is required. These things are all discussed. Yeah, my self-reduction thing came up here. Copper key, you're gonna use the self-reduction. Can use that roasting, leaching with copper also, but self-reduction is better. Reduction takes place easily. Sulfuric acid leaching is also using hydrometallurgy for low graders. Low graders. The filler point is also important. Metal may be purified by fraction. Zinc is purified by fractional distillation. Uh, Fractional distillation columns. Okay, this is not fractional distillation column. This is column chromatography in another way. The left diagram. Fractional distillation column. The diagram is a lot similar, fortunately. Below are some of the key points, ores in which one of the components. Let's see criteria for magnetic separation. 6.2 is some examples of leaching. Leaching లో ఫ్లక్స్ స్లాగ్ రోల్ ని పనిచేస్తుంది. 6.3 is the theory behind Ellingham diagram. Simple point, please. Got it. 6.4 is the case when you're gonna use the other metal to reduce not copper, not carbon or carbon monoxide. For Al2 O3, you can either use that electrolytic refining or you're gonna do it with magnesium. And there is another thing, some dynamite process or something, iron purification. You're gonna use titanium oxide and aluminum to blast it up, I guess. The dynamite process you're gonna use to weld the railway tracks. Just చిన్న డైనమైట్ అరేంజ్మెంట్ పెడతారు with that iron, aluminum and that something, and they're gonna blast it. So it's gonna blast and weld the two railway tracks. Aluminum you can use magnesium basically. So that's it for this. Sorry I didn't cover the device piece. Thank you. Bye.